limit, right? Can we evaluate it graphically? Well, shall we Desmos it? Yeah, we can Desmos it, right? I have Desmos open. I have graphed these two functions separately. I can turn them off and then start a new function. I'm going to call it h. H of x is equal to ln x over, did I put, right, instead of hitting the equal sign, I hit minus sign. So it looks like this, right? And then I want to take a limit as x approaching 1. Okay. X approaching 1 is right here. Let's zoom in a little bit. This right here, right? So, see, it's undefined, right? As you expect. However, if you go slightly to the right, it's defined. It's slightly to the, you do see why it's undefined right here, right? Because you cannot put 1 in, your denominator cannot be 0. But it sure looks like your limit is -1, right? Can we do this without the graph? That's what L'Hopital's rule is all about. Okay, I'm going to take this one out and put these two back on. So let's just think graphically. The key is both of them, see, f is the ln x, f of 1 is 0, and g of 1 is both 0. Okay, I'm gonna copy this thing. Snipping tool is not always working now. Let's just zoom into right here and we'll go back to the, okay. So when we take a limit and value of this, so limit is when x is approaching 1 but not equal to, right? Let's just take a right limit to make a point. So let's say x value, we cannot, there's a hole here, we cannot be at 1, but say we are slightly off, right? And this is the value of, I'm going to put it in red. This is the value of f of x, right? Which is ln x. X approaches that way slightly, and this is the value this way is g of x, isn't it? Which is 1 minus x. Do you see that? So if I want to take, and then this right there, that thingy, we'll call it delta x. Okay? So what I want to do is take a limit of f of x over g of x, right, as x approaching 1. Okay, now the question is it same as limit of f prime of x over g prime of x as x approaching 1? Is it? From the picture, does it look like it? A little bit this way and a little bit that way?
Yeah.
Only reason this is true is because this thing goes through x-axis right here. Right? Because it sure looks like this. df over dx over dg over dx now, doesn't it? And then after all, dx is canceled. You know what I'm saying? So that's the idea. Okay, so for now, I'm going to show you how to prove, I'm going to show you how to use it. Then I'm going to actually prove this is the case, okay? I'm going to put them right here. Okay, so this is how you use it. So when we have limit of ln x over 1 minus x, x approaching 1, what we do is, and this is known as a stronger form, instead of this one, actually I put limit again. This is more convenient. Your book has both of them. X approaching 1 of derivative of this. So we have 1 over x over derivative of this, which have -1. Good. Now, denominator doesn't become 1, so you can actually plug it in, and that gives you -1. Huh, isn't that convenient? Okay, let's do another one. Do you remember this? Yeah, okay, let's do that one. Because the answer to this was 1 now, wasn't it? Yes. Okay, let's see if we take a derivative of this and then take a limit. So x approaching 0 of derivative is cosine of x, and derivative of this is 1, right? Now we plug it in, so we have 1. Ain't that convenient, eh? Now, can we, well, then can we always take a, no. Only time this works is if it's 0 over 0 form. This becomes 0 and this becomes 0. This numerator becomes 0, this denominator becomes 0, right? So it only works in this thing called indeterminate 0 over 0. The other case it also works is if it becomes infinity over infinity. By rearranging the fraction, you can see how infinity over infinity can be rewritten as 0 over 0, right? Right. That's the only time this thing works. Otherwise, it fails. Okay, so you have to check each time. Okay, shall we prove it? Yeah. So this is L'Hopital's rule. Okay, weak form. Okay. So suppose, and this is the key. This has to be satisfied, right? And then, of course, these things have to exist. Right? Okay, and then if you take, so this is 0 over 0, both of these will approach 0. Do you see why the limit exists and it has to be 0 from these two? If the derivative exists, it means it has to be continuous, and if this thing is equal to 0, then the limit has to approach 0 as well. You know what I'm saying? Okay, I'm going to prove this. So here's a proof. Okay, I'm going to start with this thingy. So limit of f of x over g of x as x approaching 1, okay? And that is limit of x approaching 1 of f of x minus 0 over g of x minus 0. Still true? Yeah, of course it's true. And that is equal to limit of x approaching 1 of f of x minus f of, oh, did I say 1? Actually, it doesn't need to be 1, right? It's just any general a. Because up here, they just use a, okay? F of a over g of x minus g of a. Why is that true? Somebody please tell me why you get this, right? You get equal to 0. Why is this thing equal to that thing?
Because f of a equals g of a equals 0.
This, right? They are both zeros, right? That's what I have to use this given at some point. And this is the key point which makes this proof work. Therefore, this is the condition for L'Hopital's rule. Okay, now Then continue here. So limit of x approaching a of f of x minus f of a space over g of x minus g of a. Whenever math teacher leaves a space like that, it's going to insert something, right? And guess what I'm going to insert here? That and that. Okay, that is same thing as limit, right? Somebody tell me this look familiar? Ah, this new computers. What is that thingy?
It looks like the alternate form.
Oh, alternate form of the derivative now, doesn't it? Wow, voila, the proof. This is exactly what we wanted to do, right? Amazing, isn't it? But be careful, this from here to here is the key step. And this is only possible because f of a and g of a are both equal to 0. Oh, this is really annoying. You get it? Okay, Sarah.
Yeah, Mr. Kim, so how do we prove when the actual value is like infinity, which is another possible situation?
You're gonna have to trust me. But idea behind this. If you have, let's say, let's just, it's a little stupid, but I'm gonna take this kind of example. Say 2x squared over x squared, right? Actually, no, this is better. Actually, your book has this kind of, I'm gonna actually make it part of the note. Your book has this, so actually, I'm gonna take an example. Okay, what about this then? Limit of sine of 1 over x over 1 over x as x approaching infinity. No, that's same thing. No, that's not what I wanted to do. There is a nice example. I can't think of nice example.
Can we change the limit to 0 like that way?
If it approaches, yeah, let's do it this way, okay? So this is, but then numerator is not infinity, so I can't do it. So, I mean, this thing gives a nice answer, which is 0, but it does not really apply to your question. There's a, let's go back to the dumb one. Let's just do it this way, 2 over x and 1 over x, right? And then they both approach infinity. I know we'll just simplify the fraction, right? But is this thing really same as? You get the idea? You see how you can rearrange the fractions to change infinity over infinity to 0 over 0? Just flip the numerator and denominator. So these two are equivalent, but nothing else, right? So L'Hopital's rule only applies to this kind of thing. I mean, nobody would do this thing like that. We'll just simplify the fraction, but just to prove a point. Good. Okay, then we'll do a little more realistic examples. These are you. Okay, let's look at this first one. So limit of x approaching, I'm going to zoom in a little bit, pi over 2 from the left-hand side of secant x minus tangent x. You, wait a minute. There's a vertical asymptote at pi over 2 for secant as well as tangent. So do you see this is infinity minus infinity idea? What is the infinity minus infinity? Do they cancel and give you 0? No, when this happens, this thing could turn out to be anything between positive and negative infinity. You just don't know. And well, can we just use L'Hopital's rule? No, you can't, because this is infinity minus infinity, not infinity over infinity. You ideas?
We can rewrite that into the ratio
Huh?
function.
We actually, yeah, let's just do this. Do you see it yet? Where am I going with this? I'm going to find the common denominator, which is cosine of x. Good. Let's check. If I substitute pi over 2 in the denominator, that becomes 0. If I substitute pi over 2 here, then it becomes 1 minus 1, which is 0. Ah, we have achieved 0 over 0 now, haven't we? Well then, we can L'Hopitalise it. I use that as a verb form because it means hospital, right? Okay, so let's L'Hopitalise it. So that is, you can actually take a derivative and then without the limit, but like it's my habit, okay? You can just take a derivative and plug it in. So the numerator becomes negative cosine of x, and the denominator becomes negative sine of x, right? Oh, by the way, don't be differentiating over and over. I mean, this will go indefinitely. You have to check each time whether this is still 0 over 0 form, okay? So if I put pi over 2 here, denominator becomes negative 1. Numerator becomes 0. So this is 0 now. You get it? So we're done. Get it? Okay, now let's do the second one. I'm going to change the color. So limit of x approaching, or k approaching infinity of 1 plus 1 over k to the, why does that look so familiar?
Definition of E, right?
That's the definition, alternative definition of E, and then I told you someday I'm going to prove to you this is same, because our definition of E was the base of the exponential function whose derivative is same as the function, right? So today is that someday. Finally, we are in chapter 8, because when I promised in chapter 8, I'm going to show you why that's the same thing. So this better turn out to be E. Okay, do you guys still remember how to change the base of exponential function? Giant technique, followed by ln. These two are inverse functions, so whatever I put here, which is this, will appear to cancel each other and give you this original thingy back. Say yes. Okay, now k approaching infinity, I'm gonna use the rule of exponent, rule of logarithm, so I'll put that k in front. So far so good? Now let's check. If k approaches infinity, this is infinity times 0, isn't it? It becomes ln 1. So this is infinity times 0. What the hell is infinity times 0 now? Which one wins? Is it 0 or is it infinity? What do you say?
0.
Oh, when we say limit, actually it's not equal to. So if it's equal to 0, then maybe, but k is approaching 0 but not equal to. And yet, what this is, right, this is approaching infinity but not equal to, and this thing is approaching 0 but not equal to. So now which one wins? This could turn out to be anything between 0 and infinity, by the way. But we cannot L'Hopitalise it because this is infinity times 0. So we have to tweak it a little more, and we tweak it like this. A to d, I'm going to write a little bigger now, so I can 1 plus zoom in, so you can all see this tiny, tiny little handwriting. 1 over k over 1 over k. You get it? See, it was here, but if I put it in the denominator, then I can just make it a reciprocal. Now, let's see. As k approaches infinity, this thing approaches 0, ln 1 is 0. And this thing, of course, 1 over infinity is 0. So now we have achieved this form. You know what I'm saying? So we can L'Hospitalize it now, right? And then somebody might wonder, yeah, but we have e to the something. But the limit only affects k. So it's in fact same as e to the limit of that thingy. You know what I'm saying? Limit just doesn't care what's in it. It only looks for k and then just let k approach infinity. Any question about that? So we'll take a derivative. That looks hideous. I'll do the denominator, you guys do the numerator. Okay. So I have negative 1 over k squared. What do you have? Okay, so ln. So we have to put this in the denominator like this, right? And then we have to take a chain rule, and you can recycle my work. You get it? You can see why I like this strong form better, so I can keep simplifying it instead of plugging in, and that's confusing. You know what I'm saying? Okay, does this denominator cancel that thingy on the numerator? So we'll have 1 over 1 plus 1 over k. Too much fraction? Oh, come on, people. Now, k approaches infinity, so this 1 over k approaches 0. So this whole thing is equal to e, which is e. Told you so. Huh, amazing, isn't it? We'll take one more example and call it a day, and which was, where is it? That thingy. Okay, 1 plus 4x to the code. Wow, that looks really hideous now, doesn't it? Okay, I'm gonna write it here. So limit of x approaching 0 from the left-hand side, I believe it was, right? I mean, right-hand side, and then we have 1 plus sine of 4x to the cotangent. Holy cow, right? First, let's see. Up here, let's just check what kind of form this was. This form was 1, and this dies to the infinity power form, right? Okay, and this thing, likewise, this will die, so it's still 1, and cotangent has a vertical asymptote, so it's still this form. You know what I'm saying? Well, then you might say, what is 1 to the infinity power? Is it 1 or is it infinity? Clearly, if you look at it, in this case, neither, right? It could turn out to be anything between 1 and infinity. Okay, let's do this one then. So we use the chi-and-e technique. So x approaching 0 from the left, chi-and-e, followed by ln, and then we write 1 plus sine 4x to the cotangent. So far so good? And that becomes limit as x approaching 0 and e to the, I'm going to bring cotangent x to the front. Like that. And then, I'm sorry, limit of x approaching 0. Okay, and then e to the, now let's just check. 0, this is infinity, right? And this is ln1, which is 0. So we have infinity times 0 again, which is very similar to what we just did, right? So I'm going to tweak it one more time. That is too small. E. And I'm going to write it like this. ln of 1 plus sine 4x. Then let me let this guy in. Over, now don't be putting 1 over cotangent x. What's 1 over cotangent?
Tangent.
Never mind. Yes. You get it? Now let's check. X approaching 0, so numerator approaches 0, and tangent as x approaches 0 also approaches 0. So we have achieved 0 over 0 form. So we can L'Hospitalize it. I'll do the denominator, you guys do the numerator now. Okay. Limit as x approaching 0 and e, and the denominator, of course, is secant squared. Tell me what you got. I'll give you this much. Oh, come on, chain rules.
4 cosine 4x.
Or cosine 4x, right? Now, let's plug in 0 and see what we get. This denominator becomes 1, no problem there. This denominator becomes 1, still no problem there, right? And this thingy approaches 1. So what do you have? That. You get it? See, I told you this could turn out to be anything between 1 and infinity. Any questions? Number 20, let's look at this thing. If x approaches infinity, this is infinity, this becomes infinity, and this becomes infinity. So you have infinity minus infinity. Well, what kind of infinity is it? Or which infinity wins? We don't know. But what we can do is combine these two. So we'll have limit of x approaching infinity of, well, ln. ln's are nice, right? Because we can do this. You know what I'm saying? We can combine ln. Well, we have infinity over infinity, so we can L'Hospitalize this, but we all know the answer to this one, right? This thingy right there approaches 2, doesn't it? So our answer here is ln 2. How about that? Good? Yeah. Okay, number 28. Let's do number 28. I'll put them up here. So we don't have to fill the chart out. We just want to evaluate this limit, right? Sarah, that's what you wanted? I really don't want to fill this chart. Okay.
Yeah.
Yeah, so let's just evaluate the limit. So limit of x approaching 0 from the positive of x minus sine of x over x cubed. So we have this thing, numerator is a 0, denominator becomes 0. So we have a 0 over 0 form, right? So that is same as limit of x approaching 0, derivative of the numerator, 1 minus cosine of x over 3x squared. So far so good. Denominator still approaches 0, so potentially that's problematic, but numerator, this is 1 and that approaches 1, so numerator is 0 again, right? So round 2, we L'Hospitalize this yet again. So then we'll have x approaching 0, so numerator now becomes sine of x over denominator becomes 6x. So far so good? Let's see, it's 0 over 0 again now, isn't it? This one is stubborn. L'Hospitalize it one more time. So limit x approaching 0, and the numerator becomes cosine of 0, and denominator finally becomes 6. Now we can substitute, and numerator becomes 1, so we have 1/6. How about that? Good? Okay. Well then, moving on to 39. Okay. 39 is, well, we have infinity minus infinity form, right? How can we do this, right? One thought is this. Why don't we just find the common denominator? Like that. It's like, I don't like this. I don't like this too much. I have a much better plan. Why don't I just make this as a denominator? That's a common denominator. What? You see, if you multiply square root x, that's a common denominator now, isn't it? Ain't that clever? So, well, if I do that, I will have 1 minus x to the 1/2 power. So far, so good. Before you think about L'Hopitalizing it, let's just check. Denominator becomes 0. Numerator becomes 1. So this is not L'Hopitalizable. You know, it's this form, isn't it? And that, of course, is positive infinity. How about that? Okay.